Hey guys, channels like this one are rare. Most don't survive long enough to matter. If you want this one too, Patreon link is in the description.
There is a candle on the table somewhere, the kind people actually use, not for ambience, just because the power went out, and someone blows it out. The wax has shrunk. The room smells like burnt thread, and no one asks where the flame went. That is the thing, actually. Nobody asks. The phone dies and you plug it in. The fire goes cold and you add wood, or you don't, and you get a blanket instead. Food disappears. Petrol disappears. The charge in a battery drains down to zero and the screen goes black and the device sits there. Suddenly just a small heavy rectangle. All of it. Gone. You've watched energy vanish your entire life and it never once seemed strange. I think that's worth sitting with for a moment, because something did happen to that flame. Something happened to the warmth in the room and the fuel in the tank and the food you ate for breakfast this morning that became, what exactly? Heat? Motion? Some version of you walking around thinking, breathing? The body is a strange, slow machine. The energy that entered it this morning is not sitting still anywhere inside you. It is doing something. Several things. And when it's finished with whatever that is, it will keep going. In a form you probably won't notice. Most content you find online is shaped by what performs, what gets recommended, what gets clicked, what keeps people anxious enough to stay. This channel is deliberately built the other way. Every topic here was chosen because it deserves attention, not because it would trend. That independence only exists because some people actively choose to protect it. On Patreon there are over 50 episodes, research notes, audio biographies of scientists famous and forgotten, comparison files, and more. We need 24 more co-creator members to reach stable ground. If that kind of channel is worth protecting to you, the link is in the description. Here is the thing physics will eventually tell you, and it's the kind of thing that sounds simple the first time, and then you think about it later, maybe right before sleep, and it gets stranger. Energy does not disappear. Not ever. Not even a little. The flame didn't go out. It changed. The warmth in the room didn't vanish when you opened the window. It moved into the night air, thinning out across the street, dissipating into something too spread out to feel. The petrol didn't become nothing. It became motion, became heat, became a small invisible pressure against the atmosphere. Nothing was lost. It just became harder to point at. And here is the question that nobody thinks to ask, the one that is sitting underneath every dead battery and every cold cup of coffee and every blown-out candle on every table. If energy never disappears, where is it actually going? Not in a vague sense. Precisely. Where? That question turns out to be one of the stranger ones in all of physics. Not because the answer is unknown, it isn't, but because the answer, followed far enough, leads somewhere that doesn't quite feel like physics anymore. It feels like something else, something closer to the reason anything exists at all. That's where this is going, not tonight maybe, but that's the direction. For a long time, the smartest people in Europe believed heat was a thing, not a process, not motion, an actual substance, invisible, weightless, present inside every warm object the way water is present inside a sponge. They called it caloric. And for roughly a century, caloric explained almost everything they needed it to explain. This is not a story about foolish people. That part matters. Antoine Lavoisier, the same Lavoisier who identified oxygen, who helped construct the foundations of modern chemistry, who was by any reasonable measure one of the finest scientific minds of the 18th century, listed caloric in his table of chemical elements. Not as a hypothesis, as a substance. It sat there in his taxonomy alongside hydrogen and nitrogen and phosphorus, a real entry for a real thing he believed existed in the physical world. He formalized the theory somewhere between 1768 and 1787, and what he produced was not a guess. It was a coherent, internally consistent framework that had genuine explanatory power. Here is what caloric was supposed to be, a fluid, but one with unusual properties. It had no detectable mass. It was self-repelling, meaning its particles pushed against each other, which explained why heat spread outward from a source rather than clumping. It flowed spontaneously from hotter bodies to colder ones, which matched observation perfectly. When you pressed your palm against something warm and felt the warmth move into your skin, that was caloric transferring. When a fire heated a room, caloric was flowing outward through the air. The model was tidy. It had a kind of internal logic that felt to the people using it like it must be pointing at something real, and it worked in its way. Caloric theory could describe thermal equilibrium, the tendency of objects left in contact to reach the same temperature. It could account for the way some materials conducted heat faster than others by assuming caloric moved through them more easily. It even inspired early work on what would later become thermodynamics. The theory was productive. That's the uncomfortable part. Wrong frameworks sometimes are. What it could not explain was what happened when you rubbed two things together for a very long time and the heat just kept coming. There was no obvious reservoir, no store of caloric being depleted. The friction produced warmth in a way that had no ceiling, which was, if caloric was a substance, deeply awkward. A substance runs out. Caloric in those cases did not seem to. The theory handled this badly, or rather, it handled it with the particular stubbornness of an idea that has been useful for too long. There were adjustments, clarifications, qualifications, the kind of patching that a framework does when the evidence is starting to push back and the people inside the framework are not quite ready to let it go. It's hard not to have some sympathy for that. There is something almost, not admirable exactly, but recognizable, about a theory that explained so much for so long that even its contradictions get absorbed rather than confronted. Caloric was a proud idea. It had earned its place in the literature. The scientists defending it were not being dishonest. They were being human. But a cannon was about to be bored, in a Munich arsenal, by a man with a blunted tool and a specific kind of patience, and the heat that came off that operation was going to be very difficult to explain away. Munich, 1798. The arsenal is not a romantic place. It is loud in the way that large stone buildings with metal inside them are loud, a low, grinding persistence rather than a sharp noise. The smell is iron and something damp underneath it. Men are working. Cannon barrels are being bored, drilled out from solid brass cylinders into hollow tubes that can eventually hold a charge and fire a ball. It is slow, methodical work, mostly unremarkable. Benjamin Thompson is watching. Thompson, who by this point has been given the title Count Rumford by the Bavarian government for services that had nothing to do with physics, is a complicated man. American-born British loyalist during the Revolution, spy for at least two governments at different points in his life, and now superintendent of the Bavarian arsenal. He is also, despite everything else, a careful observer. And something about the boring process is bothering him. The heat, the sheer quantity of it. A blunted boring tool produces more friction than a sharp one. More friction means more heat. Everyone knows this. But the heat coming off these operations is not behaving the way caloric theory says it should. It is not diminishing. The brass is not running out of caloric, or if it is, it shows absolutely no sign of doing so. The warmth keeps coming, hour after hour. The metal gets hotter and keeps going. There is no ceiling on it that Rumford can find. He decides to make this harder to ignore. He sets up a cannon barrel in a box of water. The barrel is rotated against a blunted steel borer, deliberately blunted, specifically chosen for maximum friction and minimum cutting, driven by two horses walking in a circle. The water surrounds the barrel. A thermometer sits in the water, and then the horses walk, and the borer grinds, and nothing happens for a while except noise and slow mechanical turning, and the particular patience that a careful experiment requires. The water begins to warm. It keeps warming. After 2 hours and 30 minutes, the water boils. It actually boils, bubbling, steaming, fully boiling, powered by nothing except the rotation of a blunted tool against brass, driven by two horses, with no fire, no fuel, no chemical reaction, no obvious source of anything. Just friction, sustained, grinding, ordinary friction. Rumford writes it down. He is not excitable in his notes. He describes what happened the way someone describes a measurement, not a discovery, though it is both. He points out the obvious problem. If caloric is a substance contained within the metal, it should run out. The barrel should cool as its caloric depletes. It does not cool, it does not deplete. The heat production has no apparent limit as long as the horses keep walking. This is, he writes, a source of heat that cannot be explained by any known theory. He is right, and he knows he's right, which is perhaps why the tone of his paper is so flat. He's not triumphant. He is just noting something. A man who watched water boil in a stone room with no fire and wrote it down in careful sentences. Caloric theory does not collapse immediately after this. That is not how ideas die. They resist. They find qualifications, edge cases, reasons why the experiment might not mean what it appears to mean. The paper is read. It is discussed. It is, in some quarters, quietly set aside. But the water boiled. That part cannot be set aside. It just sits there in the historical record, inconveniently real. A cannon in a box of water, horses walking in a circle, and heat that came from nowhere a fluid could explain. Something else was happening in that room. It would take another 50 years to name it properly. James Joule grew up in a house with a brewery attached to it. This is not incidental. Brewing is, among other things, a discipline of exact temperature. A few degrees off and the fermentation goes wrong, the yeast behaves badly, the batch is lost. You learn early in that environment that small numbers matter, that the difference between close enough and exact is not always recoverable. He was homeschooled. He had for a period John Dalton as a tutor, the same Dalton who gave chemistry the atomic theory, which is the kind of biographical detail that sounds invented but isn't. And then he went back to the brewery. He ran it. He kept it running for years while also, in whatever hours remained, building instruments in rooms adjacent to the fermentation tanks and measuring things with a precision that most professional scientists of his era were not bothering to attempt. The thing he kept measuring was the relationship between mechanical work and heat. Rumford had shown that friction produced heat without limit. What he had not done, could not quite do with the tools and the setting he had, was say how much. Not in any exact sense. He knew the heat was coming from the motion. He did not know the rate of exchange. Joule wanted the rate. He wanted the number. His most well-known apparatus is almost comically simple in description. A paddle wheel inside a container of water connected by a string to a falling weight. The weight drops, the paddle turns, the water is stirred. The stirring produces friction between the paddle and the water. The friction produces heat, and the heat, very slightly, almost imperceptibly, raises the temperature of the water. Almost imperceptibly. That is the part worth pausing on. The temperature changes he was measuring were so small they barely existed on the instruments of the time. Fractions of a degree, the kind of change that most experimenters would have dismissed as noise, as error, as the thermometer doing what thermometers do when the room shifts slightly or someone opens a door. Joule did not dismiss them. He refined his apparatus. He made it more sensitive. He ran the experiment again and again. He was doing this specific, repetitive, unglamorous work, across most of the 1840s. Not a single dramatic experiment. A long series of quiet ones. What he eventually established was this. 4.2 joules of mechanical work done on 1 kilogram of water raises its temperature by 1 degree Celsius. That is the mechanical equivalent of heat. That is the number he was looking for. It does not sound like much when stated plainly. It sounds like a unit conversion. But what it actually is, what it meant in 1845 in a room near a brewery in Salford, is that mechanical work and heat are the same thing measured differently. That you can take motion, deliberate and quantified motion, and exchange it for warmth at a precise and fixed rate. Not approximately, not roughly, exactly. No caloric required, no fluid, just a falling weight and a paddle and a thermometer read carefully enough to notice a change that a less stubborn person would have ignored. There is something almost, I want to say monastic about the way Joule worked, but that is not quite right either. Monks seek transcendence. Joule seemed mostly interested in not being wrong. He had a low tolerance for imprecision that probably had nothing spiritual about it and everything to do with years of watching what happened to fermentation batches when the temperature was off by 2 degrees. His obsession was practical before it was scientific, and then it became both. He presented his results to the British Association in 1845. The reception was, by most accounts, polite and largely indifferent. He was not a university man. He had no institutional position. He was a brewer from Salford with unusually good instruments and a result that, if true, had significant implications for the way physics thought about heat. The implications took time to land. They usually do, but the number was real, 4.2. The exchange rate between motion and warmth measured in a room that smelled faintly of malt, by a man who could not afford to get temperatures wrong and so had learned over years of small adjustments exactly how to get them right. Somewhere in the Java Sea, in 1840, the light is doing something different. It is not just brighter. It has a different quality to it, a weight almost, the kind of equatorial sun that does not feel like the sun a European physician would have grown up under. It presses. It sits on the deck of the ship and on the skin of the men working the rigging, and on the surface of the water in a way that feels less like illumination and more like a slow physical insistence. Julius Robert von Meyer is on board as ship's physician. He is 25. He has no particular reputation in science. He is there to keep sailors alive on a voyage to the Dutch East Indies, which is work enough on its own, and for the first weeks of the journey he is doing exactly that, attending to the ordinary medical complaints of men living in close quarters on a long passage. Then he draws blood. It is a routine procedure. A sailor is unwell, and the medicine of the time calls for bloodletting with a confidence that later generations would find difficult to understand. Meyer performs the procedure, and the blood that comes out is the wrong colour. Not dangerously wrong, just different, brighter, more arterial in quality than venous blood from a European patient in a European climate would typically appear. He notices it. He draws blood from other sailors. Same thing. The venous blood in these men, in this heat, is a shade closer to the red of oxygenated blood than it should be. He thinks about this for a long time. The body burns food to produce heat. In a cold climate, it burns more, working harder to maintain its temperature against the chill. In a warm climate, the body needs to produce less of its own heat because the environment is already providing it. Less burning means less oxygen consumed from the blood. Less oxygen consumed means the blood returning to the heart through the veins is still carrying more of it than usual. The venous blood looks arterial because the body borrowed less from it. That is the physiology. Reasonable, explainable, a good observation with a tidy explanation. But Meyer does not stop at the physiology. He keeps pulling on the thread. If the body produces heat by consuming food, by some internal process of combustion, and if the environment's heat can substitute for that internal production, then heat from outside and heat from inside must be, in some fundamental sense, the same thing. Not similar, not analogous, the same, interchangeable, one quantity appearing in different forms. And if heat from combustion and heat from the sun are the same thing, then what about motion? A falling stone warms the ground it strikes, very slightly but measurably. Motion becomes heat. So motion and heat are also, in that same fundamental sense, interchangeable. One quantity, different forms. He is on a ship in the Java Sea, working this out from the colour of a sailor's blood, and arriving quietly without a laboratory, without the apparatus Joule is building at almost the same moment in Salford, at something that looks very much like the conservation of energy. The paper he writes about this is rejected. The reasoning is considered too speculative, the leap from blood colour to universal physics too large for the journals to take seriously. He is a ship's doctor. He does not have the right kind of credentials for the right kind of claim. He keeps writing it anyway. The idea, once it had arrived, did not seem to be something he could put down. Whether that stubbornness is admirable or just, the particular condition of someone who has seen something true and cannot unfeel it, is hard to say, honestly. Maybe there is no difference. It is worth being careful here. Not cautious in the way that hedges everything into vagueness, but careful in the way that a statement this important deserves. Slow and specific and willing to pause on the parts that are easy to slide past. The first law of thermodynamics says this: the total energy of an isolated system remains constant. That is the whole of it, 11 words, and almost every word in that sentence is doing more work than it appears to be doing. Start with isolated. An isolated system is one that does not exchange energy or matter with anything outside itself. A perfectly sealed container that lets nothing in and nothing out, no heat through the walls, no work done on it from outside, no particles escaping. In practice, truly isolated systems are difficult to construct. The universe itself is the only example most physicists would point to without qualification. But the concept matters because the law applies precisely to it. When the boundary conditions are met, the total energy does not change, not a little, not approximately, not on average. It does not change. Total energy is the second phrase worth sitting with. Not one type of energy, not the energy in one part of the system. The total kinetic energy, potential energy, thermal energy, chemical energy, all of it summed together across the whole system at once. Any one of those forms can increase, any one can decrease. What cannot happen is for the sum to shift. If the kinetic energy in one region grows, something else somewhere in the system has decreased by exactly the same amount. The accounting always balances. This is the distinction that matters most, and it is the one that gets lost most easily in casual explanation. Energy changing form is not the same as energy disappearing. They feel similar when you are watching a fire burn down to ash and cold air. The warmth is gone, the wood is gone, something has clearly ended, but nothing has ended. The chemical energy stored in the wood has become thermal energy in the air and in the ash and in the gases that rose with the smoke. The sum is the same. The forms are unrecognizable. That is the law working exactly as it should. What the law absolutely forbids is a different thing. It forbids a system producing energy that was not already there. It forbids energy vanishing without becoming something else. These are not approximations of forbidden. They are unconditional. No mechanism, no material, no arrangement of matter has ever been found that violates either prohibition in a locally testable system. Hermann von Helmholtz understood something that Joule and Meyer and Rumford each glimpsed separately. In 1847, 2 years after Joule's paddle wheel results, 7 years after Meyer's letter from the Java Sea, Helmholtz published a paper that was less a new discovery than a unification. He showed that the conservation principle was not specific to heat, or to mechanics, or to electricity. It applied to all of them simultaneously. The same law, running underneath every branch of physics, connecting phenomena that had until then been treated as separate domains. Heat and motion were not just experimentally related, they were theoretically bound, expressions of one conserved quantity that appeared differently depending on context. That shift from domain-specific rule to universal principle is what made the first law what it is now. Before Helmholtz, you had several observations that rhymed with each other. After him, you had one law with several consequences. The difference between those two things is not minor. A collection of rhyming observations can have exceptions. A universal principle, properly derived, cannot. The law does not explain why energy is conserved. That explanation would take another 70 years, and a mathematician working in a different country on a problem she had not originally set out to solve. What the law does is describe with complete precision what energy does inside any system that meets its conditions. It changes form, it moves, it distributes, but the total, always without exception, stays exactly where it started. Energy does not have a default appearance. It shows up differently depending on what it is currently doing, what it is currently inside of, what arrangement of matter it happens to be occupying at this particular moment. The same quantity, the same conserved, indestructible thing, wears completely different clothes depending on context. And the clothes are convincing enough that for most of human history, people thought they were looking at separate things. They were not. Here is what they were actually looking at. Kinetic energy is the most direct version. It is energy of motion. Any motion, at any scale, a thrown ball, a molecule of nitrogen bouncing off the inside of a sealed container, a river moving toward the sea. The amount depends on mass and on speed, and it changes continuously as those change. When something slows down, this energy does not disappear. It moves somewhere else, into heat, usually, into sound, briefly, into the deformation of whatever it hit. Gravitational potential energy is stored in position. A stone sitting at the top of a cliff has it, not because of anything the stone is doing, but because of where it is relative to the ground and the gravitational field pulling it downward. It is a kind of latent energy, patient, uncommitted, waiting for the stone to move. When the stone falls, that patience converts to kinetic energy at a rate so consistent you could set a clock by it. People did eventually. That is more or less what a pendulum is. Elastic potential energy lives in deformation. A compressed spring, a stretched rubber band held between two fingers, pushing back with that particular insistence, not threatening, just firm, a small object with an opinion about its preferred shape. When released, the stored energy becomes kinetic almost instantly. Bows and arrows are the oldest deliberate use of this conversion that survived into written history. Chemical energy is different in texture. It is stored in the bonds between atoms, in the specific arrangement of electrons that holds molecules together. And it is, in a way that the others are not, impatient. It sits in configurations that are not the lowest available energy state, held there by activation barriers, waiting for enough disruption to rearrange into something more stable. A match head, a glucose molecule inside a cell, a litre of petrol, all of them carrying energy in the form of molecular arrangements that would rather be different arrangements, given the right conditions. Thermal energy is what happens when you stop tracking individual particles and look at the collective. It is the total kinetic energy of all the atoms and molecules in a substance, their random, ceaseless, directionless motion. Temperature is not heat. Temperature is the average of that motion per particle. Heat is the transfer of thermal energy between things at different temperatures. The distinction is small and matters more than it seems. Electrical energy is carried by moving charges or stored in electric fields. In the separation between positive and negative, the potential difference that drives current through a wire. A battery stores chemical energy and converts it to electrical energy on demand. The conversion is not perfect. Some becomes heat in the wire, but the total across the whole system does not change. Electromagnetic energy travels as radiation, as waves moving through space at the speed of light, carrying energy in their oscillating fields. Visible light, radio waves, X-rays, gamma rays. All the same phenomenon at different frequencies, all carrying energy that can be absorbed by matter and converted into heat, into chemical change, into the kinetic energy of ejected electrons. Sunlight hitting a leaf is electromagnetic energy becoming chemical energy, becoming eventually everything that leaf will ever do. Nuclear energy is the form that resists casual description actually. It is stored in the binding of protons and neutrons inside atomic nuclei, held together by the strong force against the electromagnetic repulsion of all those positive charges, crammed into an almost inconceivably small space. The energy densities involved are so far beyond the chemical that comparing them feels almost dishonest. Splitting or fusing nuclei releases energy at a scale that the same mass of chemical fuel cannot approach. The sun runs on this, has been running on it for 4.5 billion years. And then there is mass energy, which is not a separate form so much as a revelation about all the others. Every object at rest contains energy simply by virtue of having mass. That energy is not stored in bonds or fields or motion. It is what mass is. A later chapter will spend more time with this. For now, the point is that mass belongs in this list, not as a curiosity, but as a full member, the one that took longest to recognize and changed everything once it was. 9 forms, 1 quantity. The transformations between them are happening everywhere, continuously, at every scale. Nothing is created in any of those transformations, nothing is lost. The costume changes, the thing wearing it does not. Imagine a wheel. It is beautifully constructed, weighted arms that swing outward on one side as they rise, generating torque, then fold back as they descend to reduce resistance. The design is elegant. The reasoning behind it is coherent internally. The man who built it believed, with what seems to have been genuine conviction, that once set in motion it would never stop. It stopped. They all stopped. Every single one across 6 centuries of attempts, in workshops and universities and royal courts and backyard sheds, built from wood and brass and iron and later from more sophisticated materials by people who were sometimes charlatans and sometimes serious engineers and sometimes, honestly, just dreamers who had noticed an asymmetry in nature that turned out not to be there. The wheel always stopped. The fluid always reached equilibrium. The magnet always pulled in both directions equally. The machine always ran down. The oldest designs are medieval. A 13th century Indian mathematician named Bhaskara II described a wheel with curved spokes partially filled with mercury. The liquid would shift as the wheel turned, he reasoned, always heavy air on one side, always driving the rotation forward. It is a genuinely clever idea. It does not work because the mercury distributes in a way that balances the torques rather than sustaining them. The wheel slows. It stops. Villard de Honnecourt, a French architect from roughly the same era, sketched a similar device with an odd number of hammers arranged around a wheel, always more falling on one side than the other, always generating net rotation. It does not work for the same fundamental reason. The geometry that appears to create an imbalance actually produces equilibrium when the full dynamics are worked through. Leonardo da Vinci drew several. He also wrote in the same notebooks that they could not work. He understood the problem before most people were willing to state it plainly. The problem is this. A perpetual motion machine of the first kind is a machine that produces more energy than it consumes, that generates a net output from no input. This is not merely an engineering challenge, it is a violation of the first law of thermodynamics. Energy cannot be created. A machine that creates it is not a machine with a design flaw. It is a machine that requires the universe to operate differently than it does. A perpetual motion machine of the second kind is subtler. It does not claim to create energy. It claims only to convert heat from a single source, a room, an ocean, the atmosphere, entirely into useful work, with no waste. This violates the second law. Heat flows spontaneously in one direction. Extracting all of it as work requires a temperature difference, a hot reservoir and a cold one. And the cold reservoir always absorbs some fraction of the energy regardless of how cleverly the machine is designed. You cannot get around this. The second law is not an engineering constraint. It is a statement about what energy does when left to its own tendencies. What is interesting, and this is the part that gets overlooked in the dismissal of these machines, is that the failures were not useless. Each one that was carefully analysed, each one that was tested honestly and found wanting, added weight to the emerging understanding that something fundamental was being violated. The failures were data. Not the data the inventors wanted, but data nonetheless. By the 19th century, the pattern was clear enough that the French Academy of Sciences formally announced it would no longer evaluate perpetual motion proposals. Not because the Academy was closed-minded, but because the accumulated evidence was sufficient. Every design submitted over several centuries had failed for reasons that pointed consistently at the same underlying truth. At some point the experiment has been run enough times. There is something almost, I am not sure sympathetic is the right word, but something in that direction, about the people who built these machines. They were not all frauds. Many of them genuinely believed they had found the asymmetry that the universe had been hiding. The idea that somewhere in the geometry of weights and leviers and magnets there was a configuration that would keep going, that would give back more than it took. It is a seductive idea. It still is. The wheel always stopped. And every time it did, the silence after told physicists something true. It told them that the accounting was real, that whatever energy went in, the same amount came out, no more, no less, never, and that no arrangement of matter had ever found a way around that. Not once, not in 6 centuries of trying. The wheel is still spinning somewhere in someone's notebook. It will stop. It always does. Göttingen, 1915. David Hilbert and Felix Klein have a problem. The problem is not embarrassing in the way that small errors are embarrassing. It is embarrassing in the way that suggests something foundational might be wrong. Einstein's general theory of relativity, the new framework for gravity, space, and time that is still being constructed and refined in these years, appears, under certain conditions, to violate the conservation of energy. Not slightly, not in ways that could be attributed to approximation or computational error. The equations, in specific cosmological contexts, seem to allow energy to appear or vanish without accounting for it. For physicists who have spent decades treating conservation of energy as bedrock, this is a serious situation. Hilbert writes to Emmy Noether. He has encountered her work and believes she is the right person for this. Klein agrees. They invite her to Göttingen. She comes, and the university immediately begins arguing about whether she should be allowed to teach. Göttingen in 1915 does not have female professors. Some faculty members object on principle. Some object on procedural grounds. Some raise concerns that are difficult to distinguish from each other, formalized into institutional language that keeps the question open longer than it has any reason to be. Hilbert is frustrated by this. He is said to have asked at one point why the university should function like a bathhouse. The question was not rhetorical. The situation continued anyway. For years, Noether lectures under Hilbert's name, her courses listed as his, her students technically attending his class, her work proceeding in the ordinary way that work proceeds when the person doing it has decided not to wait for permission. In 1918, she publishes what will eventually be called Noether's theorem. The theorem does not solve Hilbert's specific problem directly. It dissolves it. It answers a question so much larger that the original problem becomes a specific case of the answer, and the answer turns out to apply to all of physics simultaneously. The theorem says this: every continuous symmetry of a physical system corresponds to a conserved quantity. Symmetry here does not mean visual balance or geometric elegance. It means something precise and technical, a transformation you can apply to a system that leaves its fundamental behavior unchanged. If you can rotate a system and the physics remains the same, angular momentum is conserved. If you can move a system through space and the physics remains the same, linear momentum is conserved. And if you can shift a system forward or backward in time, if the laws governing its behavior are the same today as they were yesterday and will be tomorrow, then energy is conserved. That is it. That is the answer to why. Not because energy conservation was observed and then declared a law. Not because physicists decided it was probably true and built a framework around the assumption. But because the universe has a particular symmetry with respect to time, and that symmetry, by mathematical necessity, not by physical convention, produces a conserved quantity. Break the symmetry and you break the conservation. Preserve the symmetry and the conservation is not a choice. It is a consequence. The connection between these two things, between the texture of time and the behavior of energy, is not obvious. It does not feel like it should be true when you first encounter it. A statement about when the laws of physics apply, producing a statement about what energy does across all of those laws. The link between them requires mathematics that takes time to follow, but the conclusion is exact, not approximate, not philosophical, exact. Einstein called her work the most significant creative mathematical genius thus far produced. He meant it as description, not as compliment in the social sense. He was identifying what the theorem actually was, a result of a different order than the results around it. Noether herself seems to have regarded it with the particular equanimity of someone who had been doing important work in difficult conditions long enough that importance and difficulty had both become ordinary. She kept working. There was more to do. The specific problem Hilbert and Klein had asked her to look at, the apparent energy violation in general relativity at cosmological scales, turns out to be a consequence of the expanding universe-breaking time translation symmetry, which means, by Noether's own theorem, energy is not strictly conserved there. Not because the law fails, because the symmetry it depends on is not present. The theorem explained the anomaly by explaining what conservation actually requires. That is the thing about a deep enough answer. It does not just solve the problem, it tells you exactly why the problem existed. Here is a question that sounds simpler than it is. Why is energy conserved? Not how, not in what systems, under what conditions, with what exceptions at cosmological scales. Why? What is it about the universe that produces this particular constancy? This one quantity that transforms endlessly and never changes its total. The answer that physics gives is not what most people expect. It is not because matter works that way, or because we have always observed it to be true, or even because the mathematics requires it, in some abstract sense. The answer is more specific than any of those and stranger, and, once it settles, more satisfying. The answer has to do with time, with what time is like, with one particular feature of time that is so ordinary you have probably never noticed it as a feature at all. Consider this: you drop a stone today. It falls. You drop the same stone tomorrow from the same height with the same initial conditions. It falls in exactly the same way. The arc is identical. The speed at impact is identical. Nothing about Monday's stone dropping is different from Tuesday's. The rules governing the fall did not change overnight. They did not change between last year and this year. They will not change next century. This seems so obvious it barely registers. Of course the rules are the same. What else would they be? But that sameness, that specific feature of physical law, the fact that the rules do not shift as time passes, is not nothing. It is a deep structural fact about the universe. And Noether's theorem says that when a system has that kind of symmetry, when you can move it through time and its fundamental behavior is unchanged, something must be conserved. The mathematics is exact on this point. The sameness of the rules across time does not merely suggest conservation, it requires it. Energy conservation is not a rule that physicists observed and then promoted to law. It is not an axiom someone decided to build physics on top of. It is a consequence. A thing that follows necessarily from a prior fact about time. If the rules are the same on Tuesday as Monday, energy is conserved. You do not get to have one without the other. They are the same statements expressed in different languages. This changes what conservation means slightly. Or not changes. Clarifies. The universe does not conserve energy because it is following a rule. It conserves energy because of what time is like. Because the fabric of physical law does not have a preferred moment, does not treat Wednesday differently from Thursday, does not allow the equations governing a falling stone to quietly shift between observations. The constancy of energy is a shadow cast by the constancy of time, and the reverse is also true, which is the part that stays with you longer. If time were not like this, if the rules changed as the universe aged, if Tuesday's physics were subtly different from Monday's, then energy would not be conserved. Not approximately, not in most cases. It would simply not be a conserved quantity. The law would not exist. This is not a thought experiment. In the expanding universe, the rules do change as time passes. Not the local rules, but the cosmological ones. Space itself is different at different epochs. And in that context, this is, global energy conservation does not hold. Not because the law breaks down, because the symmetry it depends on is not there. Noether's theorem is not telling you that energy is conserved. It is telling you why, and under what conditions, and what would have to be different for it not to be. That is a different kind of knowledge than observation gives you. Quieter, maybe, but harder to shake. Pick up something small. A coin maybe, or a stone from a path of something that fits in the palm without effort, something the hand registers as unremarkable. Feel the weight of it, the slight familiar pressure against the skin. That object contains enough energy to level a city. Not metaphorically, not in some loosely approximate sense that physicists use to gesture at large numbers, literally, precisely in the way that physics means when it uses the word contains. The energy is in there, in the mass itself. stored in the fact of the object's existence rather than in anything it is doing or any configuration it happens to be in. This is what E = mc squared actually says, and it is not what most people think it says. The equation appears in a short paper Einstein published in 1905, a follow-up, almost an afterthought in length, to the special relativity paper from the same year. It is 4 symbols. Most people encounter it as a statement about nuclear weapons, or about the conversion of mass into energy in reactors and stars, which is accurate but incomplete. The deeper reading is quieter than that. The equation says that mass and energy are not 2 different things that can, under the right conditions, be exchanged. It says they are the same thing. Mass is energy. Energy, in sufficient concentration and the right configuration, is mass. The boundary between them is not a physical fact about the universe. It is a category that made sense at human scales, where the 2 appear so different that the connection between them is invisible. At rest, not moving, not reacting, not doing anything, a kilogram of matter contains approximately 9 × 10⁻16 joules of energy. That number is the mass multiplied by the speed of light squared, and the speed of light is large enough that squaring it produces something that strains the intuition. Roughly 25 million megawatt hours. New York City, running at its ordinary consumption, would use that energy over the course of several months, from 1 kilogram of anything, a kilogram of water, a kilogram of air, a kilogram of old newspaper. The energy is not stored in the bonds between atoms, the way chemical energy is. It is not kinetic, not thermal, not the result of any particular arrangement. It is rest energy, energy that exists because mass exists, because the object is there at all, prior to any process or reaction or structural feature. Einstein's paper did not describe a mechanism for accessing it. It described what mass is. That distinction matters more than it seems. For most of the decade after 1905, the equation was understood primarily as a theoretical result, elegant, probably important, not immediately practical. The idea that mass was a form of stored energy was remarkable, but nothing about ordinary matter suggested the energy was accessible. It sat there, in every object, at scales that made the chemical energies of ordinary reactions look like rounding errors, and for a long time there was no known way to reach it. The first conversions were observed not in laboratories but in cosmic rays, high-energy particles arriving from space colliding with atmospheric molecules and briefly converting small amounts of mass into energy and back again in particle showers that physicists were just beginning to understand. The amounts were vanishingly small, but they were real, and they matched the equation with a precision that left no interpretive room. I think the thing that is easy to miss, and I keep coming back to this, is what the equation implies about the nature of matter itself. Not what it implies about bombs or reactors or stars, but what it implies about the coin sitting in a hand, the stone on a path, the unremarkable solidity of ordinary objects. They are not simply matter in the way that older physics meant matter. They are concentrated energy, held in a form so stable that it persists without process, without reaction, without any mechanism required to keep it there. The distinction between matter and energy is a distinction that makes sense at the scale of kitchens and candles. At the scale of physics, it does not quite hold. Mass is not a container for energy. Mass is energy, taking a form that feels, at human scales, like something completely different. The coin in the hand, the stone on the path, sitting there quietly in the form that energy takes when it is not doing anything else. The sunlight on your skin right now, if it is day where you are, or if you remember what afternoon feels like, left the sun about 8 minutes ago. It crossed 150 million kilometers of vacuum without a medium to travel through, arrived at the atmosphere, scattered, warmed the air slightly and landed. That warmth is real. It is a physical transfer of energy from a star to your skin, and it happens continuously every clear day, without any mechanism visible to you, and without any obvious cost that you can observe. But the cost is there. The sun is paying for that light with mass, Not metaphorically. Every second, the sun fuses approximately 600 million metric tons of hydrogen into helium. The helium that comes out of this process weighs less than the hydrogen that went in. The missing mass, roughly 4 million metric tons of it every second, does not go anywhere in the conventional sense. It becomes energy. It becomes the light that takes 8 minutes to reach you, and the warmth that you barely register on an ordinary afternoon. 4 million metric tons per second. That number deserves a moment. It is the kind of figure that is easy to read past because it is too large to picture accurately. So consider it differently. The entire mass of Mount Everest is approximately 810 trillion kilograms. The sun converts the equivalent of roughly 5 Mount Everests into pure energy every single day. It has been doing this for 4.6 billion years. It will continue for approximately another 5 billion before the hydrogen in its core runs low enough to change the process fundamentally. The efficiency of this conversion is 0.7%. That fraction, not 7%, not even 1%, but 0.7, is the proportion of the hydrogen mass that actually becomes energy. The rest becomes helium. It goes through the fusion process and comes out the other side as a different element slightly lighter than the inputs but not converted. Only 0.7% of the mass that enters the reaction is actually exchanged for energy via E equals mc squared. And 0.7% of the mass of 600 million metric tons per second run through the speed of light squared produces approximately 3.8 times 10 to the 26th power watts of continuous power output. The number is almost insultingly large. Every second, the sun releases more energy than humanity has consumed across the entirety of recorded history. It does this at 0.7% efficiency. The other 99.3% just becomes helium and sits there in the core, accumulating, gradually building up a helium ash that will eventually matter, but not for a long time yet. The process itself is worth slowing down on. 4 hydrogen nuclei, 4 protons, are not simply jammed together into a helium nucleus in a single step. The proton-proton chain is a sequence of reactions, each probabilistically unlikely, each requiring conditions of temperature and pressure that exist inside a stellar core and almost nowhere else in the observable universe. The core of the Sun sits at roughly 15 million degrees Celsius and a pressure around 250 billion times the atmospheric pressure at Earth's surface. Under those conditions, quantum tunneling allows particles that classically should not be able to reach each other to occasionally fuse anyway. This is, and I want to be precise here because the word gets used loosely, a transformation, not a creation of energy, not a destruction of mass, a transformation of one form into another at a rate governed by the conditions of the core and the available fuel supply. The conservation law is not being set aside for the sun's convenience. It is operating exactly as it always does. Mass enters the reaction as one of energy's forms. Electromagnetic radiation exits as another. Nothing is created, nothing is destroyed. The accounting holds at stellar scale as well as it holds in a laboratory in Salford. What is strange, sitting with all of this, is how ordinary the sunlight feels. 8 minutes from a nuclear furnace converting millions of tons of mass per second, and it arrives on skin as something barely worth noticing on an unremarkable afternoon. The universe does not always scale its signals to its processes. The warmth is real. The cost behind it is almost beyond arithmetic, but the total, hydrogen in, helium and light out, mass accounted for in full, never changes, not by a gram. Somewhere in a hospital, a patient is lying inside a large machine. The room is quiet in the specific way that medical rooms are quiet, not peaceful, just empty of unnecessary sound. The machine hums. A radioactive tracer injected into the patient's bloodstream is decaying, emitting positrons, anti-electrons, the antimatter counterpart of the ordinary electron, and those positrons are travelling a very short distance through tissue before something happens to them. They meet an electron. The encounter takes no time worth measuring. The positron and the electron exist, and then they do not. In their place are 2 photons, gamma rays, each carrying 0.511 mega electron volts of energy, travelling in precisely opposite directions at the speed of light. The machine detects both photons simultaneously. From the timing and geometry of the detection, it reconstructs the location of the decay. A scan is produced. A physician reads it. The annihilation event that made it possible is not noted anywhere in the clinical record. It was a tool. It performed its function. This happens in hospitals every day. The word annihilation is dramatic in a way that the event, at the scale it typically occurs, is not. Two particles become two photons. The mass of the particles, all of it, the entire rest mass of both, converts to electromagnetic energy with a completeness that no chemical reaction approaches. No residue, no byproduct. The electron and positron are gone, and the photons carry exactly the energy the particles contained. Not approximately. The conservation is exact. The 0.511 mega-electron volt figure is the rest mass of an electron expressed in energy units. One electron at rest contains 0.511 mega-electron volts of mass energy. A positron, being its antimatter twin, contains the same. When they meet, the two photons carry 0.511 mega-electron volts each, the full rest mass energy of one particle apiece. The numbers close, they always close. What this event demonstrates, quietly, in a hospital corridor, in a piece of equipment that most patients find merely loud and claustrophobic, is something that the previous two chapters approached from different angles. E equals mc squared said that mass is a form of energy. The sun's fusion said that mass can become light if the conditions are extreme enough. Annihilation says something slightly different, and in some ways more direct. It says the border does not exist. Not that it can be crossed under sufficient pressure. Not that a matter and energy are interchangeable in principle. It says that an electron and a positron, meeting under ordinary conditions in ordinary tissue, simply become photons. No extreme temperature, no stellar core, no reactor. The conversion requires nothing except the meeting of a particle with its antiparticle. The matter does not transform under duress. It reveals what it always was. I keep finding myself wanting to say that this is remarkable. It is, but it is also, and this is the part that sits oddly, completely routine. Pair annihilation happens in cosmic ray showers in the upper atmosphere. It happens in the solar core as part of the radiation pressure that holds the sun up against its own gravity. It happens in PET scanners, in ordinary hospitals, in ordinary cities. The universe does not reserve this particular truth for special occasions. It runs on it constantly. The photons from a PET scan travel outward from the annihilation point in opposite directions because momentum must be conserved as well as energy. The initial momentum of the electron-positron pair in the centre of mass frame is zero, and the two photons moving in exactly opposite directions with equal energies sum to zero momentum as well. The conservation laws do not take turns. They apply simultaneously always, and the geometry of annihilation reflects all of them at once. What was matter is now light. What was light was always in the relevant sense energy. What was matter was also, in the same sense, energy, just wearing a different form, one that felt solid, that had mass you could measure on a scale, that felt categorically unlike radiation. The category was a human convenience. The universe never quite agreed to it. Hold something warm, a mug, a stone that has been sitting in the sun, the inside of your own closed fist after a minute or two. The warmth transfers into the skin, not dramatically, just the steady, patient movement of something from the object into you. It feels simple. It feels like one thing flowing into another. It is not one thing. It is approximately 10 to the 23rd power things, all moving at once in no particular direction. Heat is not a substance. This is the lesson Rumford pointed at and Joule quantified, and the caloric theorists could not quite let go of. There is no fluid, no caloric, no invisible medium flowing from the warm object into your hands. What is actually happening is a transfer of motion. The atoms and molecules in the warm object are moving, vibrating, jostling, colliding with their neighbours, and when that object contacts your skin, those collisions begin to transfer some of that motion to the atoms in your hand. Your hand warms because its particles speed up. The The mug cools slightly because its particles slow down by the same degree. Energy moves, nothing flows. Temperature, when you follow this down to where it actually lives, is not a property of an object the way colour or shape is. It is a statistical fact about a population. Specifically, it is the average kinetic energy per particle in a substance. A hot gas has molecules moving fast on average. A cold one has molecules moving slowly on average. The temperature you read on a thermometer is the macroscopic shadow of that average, a single number summarizing the collective behavior of a number of particles so large that individual tracking is not just impractical but meaningless. And those particles are not moving because something is driving them toward a destination. They are moving because collisions between particles redistribute momentum continuously, and the result of continuous redistribution among enormous numbers of particles is something that looks from the outside like ceaseless random motion. The atoms in the mug are not trying to warm your hand. They are indifferent in the specific way that physical processes are indifferent, following the rules of momentum exchange at each collision, producing warmth as an aggregate consequence of nothing more purposeful than that. This explains, without additional machinery, why heat flows in only one direction spontaneously. A warm object in contact with a cold one transfers energy, net energy, from warm to cold, not because warmth is attracted to coldness, because the fast-moving particles of the warm object collide with the slower particles of the cold one, and statistically, overwhelmingly transfer more momentum than they receive. Fast particles slow, slow particles speed up, the average equalizes. The process runs in one direction not because a law forbids the reverse exactly, but because the reverse requires an arrangement of particle velocities so improbable that in any system of ordinary size, it simply does not happen spontaneously. This is the edge of something. Not a cliff exactly, more like the point where the ground begins to slope and you notice the slope before you can see where it leads. The particles slowing down as they transfer energy raise a quiet question. How slow can they get? What happens as you remove heat from a substance? Cool it deliberately. Approach the point where the average kinetic energy per particle tends toward nothing. Is there a flaw? Is there a temperature at which the motion stops entirely? Classical physics would say yes. A temperature of absolute zero, motion ceased, energy at its minimum. But classical physics, it turns out, was not quite right about what minimum means. The first law does not tell you everything. This is not a criticism. It is a precise statement about what the law covers and what it leaves open. The first law says the total energy of an isolated system is constant. It says nothing about what form that energy takes, nothing about which direction transformations run, nothing about whether the energy that exists is still useful. It accounts for quantity. It is vigilant on quality. Quality needs a different law. Put an ice cube in a glass of warm water. The ice cools the water. The water warms the ice. Eventually, a few minutes depending on the size of both, the glass contains water at a uniform temperature somewhere between the two starting points. The energy in the system has not changed. Every joule that was there before is still there, distributed now across a volume of water at a single temperature, rather than split between ice at zero and water above it. The first law is satisfied completely, but something has changed, something that cannot be recovered without doing additional work on the system from outside. The cold is gone. The capacity to use the temperature difference, to run a small engine between the two, to extract useful work from the gap, is gone. The energy is all still there. The ability to do anything interesting with it is significantly reduced. This is what entropy measures. Not energy, not the absence of energy. The unavailability of it, the degree to which the energy present in a system is spread into forms and distributions from which useful work can no longer easily be extracted. Consider the burning log. Before the fire, the wood contains chemical energy, tightly organized, stored in molecular bonds that represent a relatively improbable arrangement of matter. The fire releases that energy. Heat radiates outward into the room. Gases rise. Ash remains. The total energy is conserved. It has not gone anywhere. but it has dispersed, spread into the thermal motion of air molecules across the room, into the atmosphere, into forms that are so dilute and so randomly distributed that gathering them back into a usable concentration would require more effort than the original burning provided. The energy exists. It is simply no longer available in any practical sense. Entropy always increases in an isolated system. This is the second law of thermodynamics, and it is not a corollary of the first. It is an independent fact about nature, about the direction time runs, about why some processes happen spontaneously and their reverses do not, about the arrow that points from order toward disorder in any closed system left to itself. The word disorder is common here and slightly misleading, not wrong exactly, but carrying connotations of mess that miss the point. What entropy actually tracks is the number of microscopic arrangements that produce a given macroscopic state. A glass of water at uniform temperature can be achieved by an enormous number of different configurations of individual molecules. A glass with ice at one temperature and liquid at another is a more constrained state. Fewer arrangements produce it. Systems evolve spontaneously towards states that can be achieved in more ways because those states are, in a purely statistical sense, overwhelmingly more probable. Not because nature prefers disorder, because nature has no preference, and in the absence of preference, large numbers do the rest. The second law does not contradict the first. It clarifies what the first leaves unsaid. Energy is conserved, yes, but conserved energy is not all equivalent. A joule of energy locked in a chemical bond and a joule of energy dispersed, as the faint warmth of a room at equilibrium, are the same quantity. They are not the same resource. One can do work. The other, without additional context, cannot. This is the quality problem. Energy does not disappear. It degrades. It moves, always and without exception, toward arrangements that are more probable, more dispersed, less coordinated, and in doing so it trades availability for stability. The amount stays fixed. What you can do with it does not. The ice will not reassemble in the glass. The log will not unburn. The warmth in the room will not concentrate itself back into wood. Not because the energy is gone, because the direction the universe runs is not the direction that requires it to. Rudolf Clausius wrote it down in 1865 in a formulation that has not been much improved upon since. The energy of the universe is constant. The entropy of the universe tends toward a maximum. 2 sentences. The first is the first law, the second is the second. Together they describe a universe that is, in some specific and measurable sense, running in a direction, not losing energy, never losing energy, but losing the capacity to do anything interesting with the energy it has. The implication was not lost on the physicists who read it. Lord Kelvin had already been thinking along these lines in the early 1850s, before Clausius' formulation, working from the same physical intuitions toward the same conclusion. Helmholtz arrived there too. The reasoning was not complicated once the second law was taken seriously. If entropy always increases in an isolated system, and if the universe is, at least approximately, an isolated system, then the entropy of the universe is increasing, continuously, without reversal. And entropy increasing means usable energy, energy that can drive processes, run engines, sustain the temperature differences that allow work to be done, is continuously and irreversibly converting into forms that cannot be used. The endpoint of this process has a name: heat death. It is not a violent end. That is perhaps the thing most worth noting about it. No collision, no explosion, no tearing apart of structure. Just a slow, patient equalization. Temperatures across the universe converging gradually over timescales that make the current age of the cosmos look like an opening fraction of a breath, toward a state in which everything is everywhere the same temperature. The stars will have burned through their fuel by then, long before. Black holes will have formed, and in timescales that are almost not expressible in ordinary notation, those too will have evaporated via Hawking radiation. The matter that remains will be cold and diffuse, and spread across a space that is still expanding, still cooling, approaching a thermal equilibrium that is not quite reachable but is, in the relevant asymptotic sense, the direction everything is heading. And in that state, in that distant, cold, maximally entropic future, the total energy of the universe will be exactly what it is now, not diminished, not reduced by a single joule. The conservation law will hold, as it has always held, without exception. Every joule of energy that existed at the Big Bang will still exist, distributed through an unimaginable volume of space at an unimaginably dilute concentration, in the form of photons and cold particles and gravitational fields and the faint remnant radiation of everything that ever burned or radiated or decayed. It will all still be there, every last bit of it. It will simply be incapable of doing anything. This is the distinction that the second law insists on. Energy and the capacity to use energy are not the same thing. A universe at maximum entropy is not an empty universe. It is a full universe, full of the same energy it has always contained, in which the gradients and differences and temperature gaps that allow processes to occur have all been erased. No hot place and cold place between which a current can flow. No high concentration and low concentration driving diffusion. No potential that has not already been realized. The energy exists in the only form available to a maximally entropic state, spread so thin and so evenly that nothing can be extracted from it. Late at night, when a room has been closed for hours and the heating has gone off, the air begins to flatten. Not cold yet, just losing the character it had when the heat was running, the slight warmth near the ceiling, the cooler draft near the floor. It is becoming uniform, becoming, in a small domestic way, more entropic. The energy is still in the room, it is just becoming less available. The universe is doing the same thing, over a time scale that has no sensible comparison. Clausius called it correctly. The entropy tends toward a maximum. What he did not need to add, what the physics implies without stating, is that it tends there permanently and arrives only once and does not come back. Start with what cooling actually does. When you remove heat from a substance, when you pull thermal energy out degree by degree, drawing the temperature down, what you're doing at the particle level is reducing the average kinetic energy of the atoms and molecules inside it. They slow. Their motion becomes less vigorous, less varied, the range of velocities in the population narrowing as the average drops. Cool something enough and the motion becomes very small. Cool it further and the motion becomes smaller still. The natural extrapolation, the one that classical physics arrived at without particular difficulty, is that at some sufficiently low temperature, the motion stops entirely. The particles settle, everything comes to rest. Energy, at its minimum, reaches zero. That temperature even has a name, absolute zero. Minus 273.15 degrees Celsius. The point at which classical thermal motion ceases. Classical physics was not wrong to identify this as a limit. It was wrong about what happens there. The problem is a deep one, and it does not come from thermodynamics. It comes from quantum mechanics, from a feature of the quantum world that has no analogue in the classical picture, and that took physicists time to absorb fully even after it was stated. The Heisenberg uncertainty principle says that certain pairs of physical properties, position and momentum being the central pair, cannot simultaneously have precise definite values, not because measuring one disturbs the other in some mechanical sense that better instruments could avoid, but because the universe does not allow a particle to possess both at once. Precision in position means genuine indefiniteness in momentum. Precision in momentum means genuine indefiniteness in position. This is not an epistemic limitation. It is an ontological one. Now consider what it would mean for a particle to have zero energy. Zero kinetic energy means zero momentum. The particle is completely still. And if it is completely still, its momentum is exactly zero, which means its momentum is precisely defined. But a precisely defined momentum requires a completely undefined position. The particle could be anywhere. These two requirements, being at rest at a specific location inside a material, cannot be simultaneously satisfied. The mathematics will not allow it. A particle that is somewhere specific cannot have exactly zero momentum. A particle with exactly zero momentum cannot be anywhere specific. The consequence is unavoidable. Every quantum system has a minimum energy greater than zero, not approximately greater, strictly greater, by an amount determined by the system's geometry and mass. This irreducible minimum is called zero-point energy, and it cannot be removed. Not by cooling, not by any physical process. It is not a residue of imperfect technique. It is the floor, the lowest rung of the energy ladder, below which the system cannot descend because descending would require a precision the universe has structurally prohibited. At absolute zero, a quantum particle does not stop moving. It cannot stop moving. It occupies the zero-point energy state, which is not a state of rest but a state of minimum allowed activity, the quietest the universe permits, which is not quiet at all in any classical sense. This applies not just to particles and materials, but to the vacuum itself. Empty space in quantum field theory is not genuinely empty. It is a quantum system with its own zero-point fluctuations, fields that cannot be exactly zero, because zero would constitute a precisely defined field value at every point simultaneously, which the uncertainty principle forbids. The vacuum seethes with activity that cannot be switched off, cannot be shielded against, cannot be reduced further. It is the background hum of the universe's inability to be perfectly still. The floor exists, nothing reaches it. Not a cooled gas in a laboratory, not a superconductor at millikelvin temperatures, not the void between galaxies. Everything sits above the floor, by exactly as much as the uncertainty principle requires. Whether this is strange depends on what you expected matter to be like at its quietest. If you expected stillness, a system finally at rest, motion finally absent, then yes, it is strange. The universe does not offer stillness, it offers a minimum, and the minimum is not zero. Two metal plates, uncharged, parallel, separated by a gap so small it is measured in nanometers, a few millionths of a millimeter, a distance that has no tactile equivalent at human scale. No electric charge on either plate. No magnetic field, no fluid between them, no mechanism by any classical account for one to exert a force on the other. They attract. The force is small. At separations of around 10 nanometers, it is roughly equivalent to 1 atmosphere of pressure. Not negligible, not at that scale. As the plates move apart, the force drops sharply, falling with the fourth power of the separation distance, becoming undetectable at distances above a few micrometers. But in the range where it operates, it is real, it is consistent, and it has been measured in laboratories with sufficient precision to confirm its magnitude against the theoretical prediction to within a few percent. Hendrik Casimir predicted it in 1948. The measurement came later, improving in precision through the 1990s as laboratory techniques caught up with the theory. The effect now carries his name. The mechanism is this. The vacuum, as the previous chapter described, is not empty. It is filled with zero-point fluctuations, electromagnetic field modes oscillating at their minimum allowed energy, present everywhere at all frequencies continuously. These fluctuations exist in the space between the plates and in the space outside them. But the plates impose a constraint. Between two parallel conducting plates, only electromagnetic modes whose wavelengths fit a whole number of times into the gap can exist. Long wavelengths, those larger than the plate separation, are excluded from the interior. Outside the plates, no such restriction applies. Every wavelength is present. The result is a pressure imbalance. Outside the plates, the full spectrum of vacuum fluctuations pushes inward from both sides. Between the plates, the suppressed spectrum pushes outward with less force. The net effect is a pressure directed inward. The plates are pushed together by the difference between the unrestricted vacuum outside and the restricted vacuum within. No charge, No field applied externally, just the geometry of the gap and what that geometry does to the available modes of the quantum vacuum. This is not, despite how it might sound, a subtle or disputed result. The Casimir effect is used in engineering. At nanoscale separations, the distances relevant to microelectromechanical systems, the tiny moving parts inside certain sensors and devices, Casimir forces are large enough to cause components to stick together or deflect unexpectedly. Engineers working at those scales have to account for it. It appears in design calculations. It is, in that entirely mundane sense, an applied consequence of zero-point energy. I find this genuinely difficult to get past, and I mean that precisely, not as emphasis. The vacuum exerts a force on metal plates because the vacuum is not empty. The force is predictable, measurable, and consequential at engineering scales. These are not separate claims to be evaluated individually. They are one claim, and the engineering applications are the part that makes the others undeniable. A theoretical curiosity can be interpreted, argued over, set aside. A force that makes components in a device malfunction cannot. Zero-point energy is not a hypothesis. The Casimir effect is not an anomaly awaiting explanation. The vacuum between those plates is doing something, pressing however faintly, however precisely, however exactly as Casimir's equations predict, and that something is the irreducible activity of a quantum field that cannot be brought to rest. The plates attract because the nothing between them is not quite nothing, it never was. At minus 269 degrees Celsius, helium is a liquid. Cool it further. Take it all the way to absolute zero, or as close as laboratory equipment can manage, which is very close indeed, within millionths of a degree. It remains a liquid. The temperature at which every other known substance has long since become solid. Helium sits in its container with a surface so still it is almost invisible, colourless, behaving in no way like something that should still be flowing. Under normal atmospheric pressure, helium does not solidify, not at any temperature. Classical physics has no explanation for this. Classical physics says that as temperature falls, thermal motion decreases, and at some sufficiently low temperature, the atoms of any substance lose enough kinetic energy that the attractive forces between them, however weak, win out, and the atoms settle into the fixed positions of a solid lattice. For helium, with its very weak interatomic attractions, that temperature should be low, but it should exist. The atoms should eventually slow enough to be captured. They do not slow enough. They cannot. Helium atoms are light, among the lightest of all atoms, and light particles have large zero-point energies. The uncertainty principle, applied to a helium atom confined near a lattice site, produces a minimum kinetic energy that is simply too large for the interatomic attractions to overcome. The atom cannot be localized into a fixed position without possessing enough momentum to immediately disrupt that position. The quantum floor, for helium under normal pressure, sits above the energy required for solidification. The lattice cannot form because the atoms cannot be still enough for it. This is not a failure of cooling. It is not an impurity in the sample or a flaw in the equipment. It is the zero-point energy of the helium atom exceeding the binding energy of the solid phase, and it happens at every temperature down to absolute zero and below, into a regime that temperature as a concept cannot reach. To solidify helium, you do not cool it further. You compress it. Apply roughly 25 atmospheres of pressure, and the atoms are forced close enough together that the interatomic attraction finally dominate the zero-point motion. The lattice forms, the solid exists, but it required pressure to override what temperature alone could never achieve, the irreducible quantum motion that kept the atoms from settling. A laboratory duber of liquid helium, sitting at near absolute zero, is a visible consequence of the Heisenberg uncertainty principle, not a dramatic one, not a glowing or noisy or obviously strange one, just a colourless liquid in a container, remaining liquid when everything about the temperature says it should not be, because the atoms inside it carry an energy that the universe will not let them put down. The surface catches the light occasionally, briefly, and then loses it again. The helium stays liquid. The floor holds. In the year 380,000 after the Big Bang, the universe cooled enough for electrons and protons to combine into neutral hydrogen atoms for the first time. Before that moment, the universe was opaque, a plasma so dense that light could not travel freely through it, scattering off charged particles almost immediately after being produced. When the plasma became neutral gas, the scattering stopped. Light that existed at that moment was suddenly free to travel. It began moving through space in all directions, carrying the energy it had at the moment of release. That light is still traveling. It is arriving at Earth right now, from every direction simultaneously, as a faint microwave signal spread uniformly across the entire sky. It has been travelling for approximately 13.8 billion years. In that time, space itself has expanded by a factor of roughly 1,100, and the wavelength of that light has expanded with it. Wavelength and energy are inversely related for a photon. A longer wavelength means lower energy. The light released at recombination had wavelengths characteristic of a plasma at about 3000 Kelvin, hot, energetic, in the visible and near-infrared range. The light arriving today has a wavelength stretched to the microwave range, corresponding to a temperature of approximately 2.7 Kelvin. The photons have lost roughly 99.9% of the energy they carried when they were released. Here is the question that the previous 19 chapters have been quietly building toward, the one that the conservation law makes unavoidable. Where did that energy go? Not approximately, not in a hand-waving sense. Where specifically is the energy that those photons carried at recombination and do not carry now? If energy cannot be destroyed, if the total in any isolated system remains constant, then 99.9% of the energy of the cosmic microwave background must have gone somewhere. It must be accountable. The law does not have exceptions for cosmological distances or large timescales. The law does not have exceptions at all, or it is not the law. And yet, the honest answer, the answer that physicists give when they are being precise rather than reassuring, is that it did not go anywhere in any sense that the conservation law can straightforwardly account for. The energy is simply lower. The photons are redder, carrying less energy per photon, and the difference between what they carried then and what they carry now is not deposited anywhere, is not stored in any other form, is not recoverable. It is gone in the specific and uncomfortable sense that no accounting entry exists for it. This is not a small admission. It is not a rounding error or a measurement limitation. It is a genuine feature of the physics of an expanding space-time, and it sits awkwardly next to 11 words that have held up everywhere else they have ever been tested. I want to be careful here. And I notice I want to be careful, which is itself a signal worth attending to. The temptation is to resolve this quickly, to offer a framework that makes it feel tidy. Some treatments of this topic say the energy goes into the gravitational field. Some say global energy is simply not defined in general relativity, making the question malformed rather than unanswered. Both of these contain truth. Neither of them feels fully satisfying, at least not in the way that the conservation law usually feels satisfying. Complete, closed, exact. The CMB photons are real. Their energy at recombination is calculable. Their energy today is measurable. The difference is large, and where it went is not a question with a clean answer that matches the precision of the question. What this means for the conservation law is the subject of the next chapter. The short version, and it is genuinely short, is that Noether's theorem, which gave the deepest explanation for why energy is conserved, also contains the explanation for why it is not conserved here. The symmetry that produces conservation is present in local physics. In an expanding universe at cosmological scales, it is not. The law does not break. The condition the law depends on does, but that distinction, the first time you encounter it, does not feel like the relief it perhaps should. The light left 380,000 years after the beginning of everything, carrying energy that 13.8 billion years of travel has almost entirely erased and the universe's best accounting system has no entry for where it went. That is just what happened. The universe does not always balance in ways that feel like balance. The previous chapter left something open deliberately. The CMB photons losing 99.9% of their energy over 13.8 billion years of travel with no accounting entry for where that energy went. This was not presented as a solved problem, because it is not one in any simple sense. But the explanation does exist. It was given in Chapter 9, fully and exactly, by a mathematician working in Göttingen in 1918 on a different problem. The pieces are already in place. This chapter assembles them. Noether's theorem says that conservation laws are not freestanding facts about nature. They are consequences of symmetries. Each conserved quantity has a corresponding symmetry, and if the symmetry is present, the conservation follows necessarily. If the symmetry is absent, the conservation does not follow. This is not an approximation or a philosophical position. It is a mathematical result, exact and conditional. The symmetry that produces energy conservation is time translation symmetry, the laws of physics being the same today as they were yesterday, the rules not shifting as time passes. Now consider what the expanding universe actually is. The universe today is not the same as the universe 1 billion years ago. Not in the superficial sense that different things are in different places, in the structural sense that the space itself is a different size. The scale factor, the quantity that describes how large the universe is relative to some reference time, was smaller then. The density of matter and radiation was higher. The curvature of space-time was different. The background against which all physical processes occur was, in a precise and measurable way, not the same. This means the laws governing a physical system in the universe 1 billion years ago were operating in a different space-time geometry than the laws governing the same system today. Not different laws, the same underlying equations, but those equations, applied to a different background geometry, produce different effective behavior. The rules, in the sense that matters for Noether's theorem, were not the same then as now. Time translation symmetry at cosmological scales is broken by the expansion itself. And if time translation symmetry is broken, if you cannot shift the universe forward in time and find the physics unchanged, then by Noether's own mathematics, energy is not conserved. Not approximately conserved, not conserved with a small correction term, simply not conserved in the strict sense at cosmological scales. This is worth sitting with, because it is not a failure of the conservation law. It is the conservation law working exactly as Noether described it, correctly identifying the conditions under which a conserved quantity exists, and correctly predicting that outside those conditions it does not. A law that applies when its conditions are met and does not apply when they are not is not a broken law. It is a precise one. The discomfort, and there is some, the previous chapter was honest about that, comes from expecting conservation of energy to be unconditional. From the way it presents itself in every local context, every laboratory, every particle accelerator, every stellar spectrum, where the symmetry holds and the conservation follows without exception. That universal local reliability creates an expectation. The expanding universe does not meet the expectation because it does not share the symmetry. Return to that room that has changed temperature while you were away. The air is different. Whatever was true about the thermal equilibrium of that room when you left is not true now. The system evolved. Its background conditions changed. Expecting the energy accounting to close in exactly the same way as when you left is expecting the room to have stood still. It did not stand still. The universe has not stood still for 13.8 billion years. Its geometry has changed continuously. The CMB photons that left their source at recombination have been travelling through a space-time that was different at every point along their journey. Not wildly different at any given moment, but cumulatively over that distance and that time profoundly different. Their wavelengths stretched with space because space stretched. Their energy dropped because energy, in this context, is not protected by a symmetry that the expansion has already broken. The law is not silent because it failed. It is quiet here because the condition that makes it speak, the sameness of the rules across time, is not present at this scale. Noether's theorem gave the deepest answer to why energy is conserved. It also gave, precisely and without requiring amendment, the answer to why it sometimes is not. Both answers were in the same paper, published in 1918, by a woman who was technically lecturing under someone else's name. The theorem was complete, it was always complete. Something is accelerating the expansion of the universe. This has been known since 1998, when two independent teams studying distant supernovae found that the expansion is not slowing down under gravity as expected, but speeding up. The discovery was significant enough that it earned a Nobel Prize in 2011. The cause of the acceleration has a name, dark energy, and almost nothing else about it is settled. What is known observationally is this. Dark energy appears to be distributed uniformly through space. Its density, the amount of it per unit volume, does not decrease as the universe expands. This is already strange. Ordinary matter becomes less dense as space grows, because the same amount of matter occupies a larger volume. Radiation becomes less dense even faster, losing energy to redshift as well as spreading out. Dark energy does neither. As the universe expands, the dark energy density per cubic meter stays approximately constant, which means the total amount of dark energy in the universe is increasing. More space at the same density is more dark energy, not redistributed dark energy, not dark energy that was somewhere else and has moved. More of it in a growing volume with no identified source. This is the most uncomfortable fact in modern cosmology. Not because it is paradoxical in the logical sense, the mathematics handles it without internal contradiction, but because it sits at the edge of what the conservation of energy means at cosmological scales, and at that edge, the view is not reassuring. The first framework physicists use to think about this is the cosmological constant. Einstein introduced it in 1917 as a term in his field equations representing a constant energy density of empty space, not matter, not radiation, just the vacuum itself carrying a fixed energy per unit volume. He later called it his greatest blunder when the expansion of the universe was discovered and he felt the constant was no longer needed. It was reinstated after 1998. In this framework, dark energy is simply a property of space-time. The vacuum has an intrinsic energy density. It has always had it. And as the volume of space grows, the total energy of the vacuum grows with it. There is no source because the vacuum does not require one. It simply is what it is, and what it is includes energy. The second framework is dynamical dark energy, the idea that dark energy is not a fixed property of space-time but a field, varying slowly across space and time, with a density that happens to be approximately constant at the current epoch, but may have been different in the past and may change in the future. This framework has the advantage of being potentially testable. If dark energy is a field, its behavior might deviate measurably from a pure cosmological constant over sufficiently long baselines. Current observations have not decisively detected such a deviation. They have also not ruled it out. Neither framework explains where the energy comes from. The cosmological constant does not explain it. It assumes it as a property of the vacuum whose value must be measured rather than derived. Dynamical dark energy models push the question back a step. There is a field, the field has energy, but the origin of the field and why its current density has the value it does remain open. The honest position is that physicists do not know what dark energy is. They know what it does. It accelerates expansion. Its density is approximately constant. The total amount of it is growing. And they have two broad categories of framework for thinking about it, neither of which is proven and both of which leave the deepest question unanswered. Where is the energy coming from? I have no clean answer to offer here, and I want to resist the temptation to gesture toward one. The conservation law, as the previous chapter explained, does not strictly apply at cosmological scales where time translation symmetry is broken, so dark energy increasing does not violate a law that applies here. But not violating a law is different from being explained. The energy grows. The universe does not annotate the process. The dark at the edge of the lit room keeps moving outward. Where it comes from is not a question the room can answer from the inside. A black hole looks, from the outside, like the end of accounting. Matter falls in, light falls in. Information about the state of every particle, every quantum number, every configuration of energy that crosses the event horizon, all of it falls in, and the event horizon closes over it the way water closes over something dropped from a boat. The surface shows nothing. The interior is causally disconnected from the rest of the universe. Whatever went in is gone, in the most complete sense the word can carry, not gone to somewhere else, not transformed into something detectable, but beyond any horizon from which a signal could return. This appears to be a problem for a law that says energy cannot be destroyed. The appearance is misleading. On the energy question, the situation is actually resolved, and not easily, not without requiring quantum mechanics applied at the boundary of a relativistic object, but resolved. On a different question, the situation remains one of the deepest open problems in theoretical physics. These two things, the energy question and the other question, are worth keeping carefully separate, because they have different answers and the temptation to conflate them is strong. Stephen Hawking showed in 1974 that black holes are not completely black. Working through the behavior of quantum fields in the curved space-time near an event horizon, he found that the horizon produces radiation, a steady emission of particles and their antiparticles created from vacuum fluctuations at the boundary between the inside and the outside. One member of a pair falls inward, past the horizon. The other escapes outward, carrying energy away from the black hole. The black hole, losing energy continuously to this radiation, slowly loses mass. Over timescales so long they make the current age of the universe look brief, it shrinks. Eventually, it evaporates completely. The energy that went in comes back out, not in the same form, and the radiation is thermal, a spectrum of particles at a temperature determined by the black hole's mass, but in a form that is fully accounted for. The total energy radiated over the black hole's lifetime equals the mass energy of the hole itself, plus whatever fell into it across its history. The conservation law holds, the accounting closes, this is the part that is settled. What is not settled is what happens to the information. Every physical system carries information, not in the colloquial sense of data, but in the precise quantum mechanical sense of the specific quantum state of every particle it contains. In ordinary quantum mechanics, this information is conserved. Physical processes are reversible at the fundamental level. Given the final state of a system, you can in principle reconstruct the initial state. This is called unitarity, and it is one of the foundational requirements of quantum mechanics. The problem with Hawking radiation is its thermal character. Thermal radiation is random. It carries no record of what produced it. A black hole formed from collapsing hydrogen and a black hole formed from collapsing gold of the same mass would, according to Hawking's original calculation, emit identical radiation. The information about what fell in is not encoded in what comes out. When the black hole finishes evaporating, that information has no remaining physical carrier. It appears to be gone, not transformed, not hidden, gone. This would break unitarity. And breaking unitarity does not stay contained in the black hole sector of physics. It cascades, undermining energy conservation through subtler channels, destabilizing the probability framework that quantum mechanics depends on, producing a physics that is internally inconsistent in ways that cannot be locally quarantined. Susskind, Hawking, Penrose, and many others have spent decades on this. The arguments were serious and the stakes were real. The current consensus, and consensus is the right word, not certainty, leans toward information being preserved. The holographic principle, black hole complementarity, and more recently the island formula in quantum gravity calculations all suggest that Hawking's original calculation missed something, that the radiation is not purely thermal, that the information is encoded in subtle correlations across the radiation that emerge only when the calculation is done more carefully. The information comes out, just not obviously, but this is not proven. The mechanism by which information escapes, if it does, is not understood in the way that Hawking radiation itself is understood. The energy accounting closes. The information accounting is still being written. A black hole takes everything that falls in and eventually returns it as energy. What it does with the story of what fell in, with the quantum identity of every particle, every state, every configuration that crossed the horizon, is a question the universe has not yet been made to answer clearly. The rule survives the black hole. What the black hole does to everything else the rule depends on is still being worked out. There is a difference between a law that has never been contradicted and a law that cannot be contradicted. Physics is careful about this distinction, or tries to be. Conservation of energy belongs to the first category. It has never been contradicted in any locally testable physical system across the entire history of experimental science. Whether it belongs to the second category is a philosophical question that physics, strictly speaking, cannot answer. What it can do is describe the record. The record is long. Start where the story started. Rumford's cannon boring in 1798 was not a precision experiment. It was a qualitative demonstration that heat could be produced without limit from mechanical work, with no detectable loss of mass. The caloric theory could not accommodate it. The conservation framework once built could. The experiment did not measure energy to many decimal places. It established, beyond reasonable doubt, that a particular wrong theory was wrong. That is a kind of precision too. Joule's paddle wheel experiments in the 1840s went further. He measured the mechanical equivalent of heat, 4.2 joules per calorie, with an accuracy of approximately 1% using equipment built in rooms adjacent to a brewery. That precision for the instruments and techniques of the 1840s was extraordinary. Subsequent repetitions of the experiment, with better equipment and more controlled conditions, confirmed the value. The number did not shift as measurement improved. It held. Nuclear reactors operate on the conservation of mass energy. The energy output of a reactor is calculated from the mass deficit between the input fuel and the output products, using E equals mc squared. These calculations are not approximate guides to reactor design. They are the engineering. Reactors built to specifications derived from energy conservation produce the power output those specifications predict reliably at facilities across the world. A discrepancy in the conservation law would appear as a discrepancy in reactor output. No such discrepancy has been found. Particle accelerators test conservation at collision energies far beyond anything available in ordinary matter. At proton-proton collisions at energies of several trillion electron volts produce showers of secondary particles whose energies are measured individually and summed. The total energy before collision, within the precision of the detectors, equals the total energy after. This is not a single experiment. It is the result of decades of measurements across multiple accelerators and detector generations. The precision involved is now better than 1 part in 10,000 for individual collision events, and the conservation law has not shifted by a detectable amount in any of them. Stellar spectroscopy applies the same accounting at astronomical scales. The luminosity of stars, the total energy output per second, is calculated from the mass conversion rates implied by nuclear fusion. The spectroscopic observations of stellar composition, combined with models of the fusion processes operating inside different star types, produce energy output predictions that match observed luminosities across the range of stellar masses and ages we can measure. The conservation law is doing the same work at stellar scale that it does in a laboratory and producing consistent results. Precision tests in atomic and molecular physics reach sensitivities that make the earlier experiments look approximate by comparison. Measurements of atomic energy levels, the specific frequencies of light emitted or absorbed when electrons change states, are consistent with energy conservation to better than 1 part in 10 to the 15th. That is a precision so fine that writing it out in full requires 15 zeros after the decimal point. The conservation law holds at that resolution. I think what is worth saying plainly, here at the end of this list, is that no amount of experimental confirmation proves a physical law in the mathematical sense. The next experiment could, in principle, find a violation. That is what it means to be an empirical claim rather than a logical one. But there is a point at which the weight of evidence changes the practical status of a claim. Not its logical status, its practical one. A law tested at 15 decimal places across every physical domain, from subatomic to stellar, without a single confirmed exception across 2 centuries of increasingly precise measurement, is not merely a well-supported hypothesis. It is the kind of claim that, if violated tomorrow, would require the complete reconstruction of everything built on top of it. That is a different epistemic position than most claims in science occupy. The record is not proof, but it is not nothing either. The previous chapter was about the experimental record. This one is about something slightly different, about why the experimental record, extensive as it is not actually the deepest reason physicists trust the conservation of energy. Trust built purely on observation has a particular vulnerability. Every observation confirms the law up to the precision of the instrument and the conditions of the test. A future observation, at higher precision or in untested conditions, could in principle find something different. This is the ordinary situation for empirical claims, and it is a reasonable situation. Science is not in the business of certainty, and laws that have held for 2 centuries have held for 2 centuries, not forever. The track record is strong. It is not foundational in the logical sense. What is foundational in a way that changes the character of the trust is Noether's theorem. The theorem does not merely explain why energy is conserved. It specifies the preconditioned time translation symmetry, the invariance of physical law across time, and shows that conservation is a necessary consequence of that precondition. This means that asking whether energy conservation might fail in local physics is equivalent to asking whether time translation symmetry might fail in local physics. The 2 questions are the same question, stated in different languages. And time translation symmetry failing locally would not be a small thing. It would mean the laws of physics at this moment are different from the laws of physics a second ago. Not different in some subtle high-energy regime that ordinary experiments cannot reach. Different here, now, at the scales where every quantum field theory calculation is performed, where every particle interaction is modelled, where the standard model of particle physics operates and has been tested to extraordinary precision. Every calculation in quantum electrodynamics, the most precisely tested theory in the history of science, assumes time translation symmetry implicitly. Every Feynman diagram, every scatter in amplitude, every predicted particle mass and decay rate that has been confirmed by experiment. If the symmetry breaks locally, the calculations break, not in some contained sector that can be patched while the rest continues. The framework that produces the predictions does not function without the symmetry the predictions depend on. This is what I mean by structural. Energy conservation is not one pillar among several in modern physics. It is embedded in the foundation shared by all the pillars. Removing it requires removing the foundation. What stands above it, quantum field theory, the standard model, general relativity in its local limit, the entire predictive apparatus of modern physics, does not stand without it. Physicists are not looking for local violations of energy conservation, not because they are incurious or because the question seems settled by the habit. Because a violation would require simultaneously explaining why time translation symmetry is broken in a system where quantum field theory calculations, which depend on that symmetry, continue to produce predictions that match experiment. The 2 facts cannot coexist. A violation of conservation implies a violation of symmetry implies a failure of the theoretical framework that produces every other successful prediction. The search for a local violation is not a productive research direction, because a confirmed violation would not be an anomaly requiring explanation. It would be a collapse requiring reconstruction. The confidence is not assumed. It is earned through the specific architecture of what the law is connected to. You could, in principle, decide not to trust it. But deciding not to trust energy conservation locally means deciding not to trust the theoretical framework built on top of it. And that framework has produced, among other things, the precise predictions of quantum electrodynamics, confirmed to 1 part in 10 to the 12th, and the standard model predictions of particle masses confirmed at colliders across decades of operation. The trust is proportional to the connections. The law is trusted completely because it is connected to everything else that is trusted. Pull one thread and you are holding the whole fabric. That is not faith. That is how load-bearing structures work. The fire goes out, the wood is ash and the warmth is gone and the room is colder than it was an hour ago. This is loss, in the ordinary sense of the word. The thing that was there is no longer there, the comfort it provided is finished. The fuel is spent. It feels like an ending because it is one, in the way that all specific configurations of energy eventually end. But the ending is not what the conservation law is about. The conservation law is about what happened to everything that was in that fire. And what happened to it is still happening right now, in forms that have moved far enough from their origin to be unrecognizable. The heat that left the burning wood entered the air in the room. Some of it left through the walls, into the night outside. Some of it warmed the objects nearest the fire. The floor, the furniture, your skin if you were sitting close, by small amounts that have since distributed further, moving outward through contact and radiation into the broader thermal bath of the world. The light the fire emitted travelled at the speed of light in all directions, some of it absorbed by surfaces in the room, converted to tiny increments of heat, some of it escaping through windows or gaps and continuing outward into the dark. The carbon dioxide and water vapour that rose with the smoke are somewhere in the atmosphere. The ash on the hearth contains the mineral components of the wood that did not combust. None of it is gone, not a joule. The accounting is perfect. It is simply that the energy is moved into forms and distribution so spread out, so thoroughly mixed into the larger system, that reconstructing what they came from is not practically possible. Here is what I keep coming back to, and I want to be precise about this rather than simply poetic. The conservation law is usually presented as a restriction. Energy cannot be created, energy cannot be destroyed. These are the things the law forbids, and it does forbid them, but that framing points in the wrong direction. The law is not primarily about prohibition, it is about description. What the universe does, not occasionally, not in special circumstances, but always, at every scale, from electron-positron annihilation to the nuclear furnace of the sun to the slow cooling of a room at a night, is transform. Energy moves between forms continuously and without pause. Kinetic to thermal, chemical to electromagnetic, mass to radiation, radiation to chemical, when light strikes a leaf and drives photosynthesis, which built the wood that is now ash. The transformations chain into each other across time in ways that are not always traceable but are always complete. The conservation law does not constrain these transformations. It describes them. It says that through all of this, through every death of a star and every cooling fire and every photon stretched thin by 13.8 billion years of travel, the quantity itself does not change. The rearranging is total. The quantity is fixed. A star exhausts its hydrogen. The nuclear burning stops. The outer layers collapse or disperse depending on mass. The light the star produced over billions of years has already left, already travelled outward, already been absorbed by planets or dust clouds or the intergalactic medium, already become something else. The star does not disappear. It becomes. The fire does not go out, in the sense that matters. It becomes the temperature of the room and the temperature of the night outside the room and the warmth of the ground beneath the building, thinning and spreading until it is indistinguishable from the ambient thermal energy of everything around it. It is still there. You just cannot feel it anymore. At the beginning, if beginning is the right word for a moment before which time as a concept may not apply, the universe contained everything it will ever contain, not everything it would ever become, not every form it would wear across the following 13.8 billion years of expansion and cooling and structure formation. But the total quantity, the conserved amount that Noether's theorem says cannot change while time translation symmetry holds, was set at that moment or before it, or in whatever process produced the conditions from which expansion followed. Every joule of energy that exists in the observable universe today was present then, in conditions of temperature and density so extreme that the former's energy takes at human scales, chemical bonds, thermal motion, the nuclear structure of atoms, did not yet exist as categories. The universe cooled. This is what expansion does to the energy it contains. It distributes it across a growing volume, reducing the density, allowing lower energy configurations to become stable. Quarks combined into protons and neutrons. Protons and neutrons combined into the first atomic nuclei, hydrogen mostly, with some helium and a trace of lithium, in the first 3 minutes. The universe was still too hot for electrons to settle into orbits. That took 380,000 years, and when it happened, light was released. The light that became the CMB, stretched now to microwave frequencies, still arriving from every direction as the oldest directly detectable signal the universe has produced. Gravity gathered the hydrogen. Slowly, over hundreds of millions of years, density variations in the early universe, fluctuations smaller than the width of an atom, scaled up by expansion, pulled matter together into the first structures. Gas clouds collapsed. At the centers of the densest ones, pressure and temperature rose until the conditions for nuclear fusion were met and the first stars ignited. The hydrogen that had been cooling in the dark for hundreds of millions of years began converting to helium, releasing the mass deficit as light and neutrinos, radiating outward into a universe that had not seen starlight before. Those stars burned. They synthesized heavier elements in their cores, carbon, oxygen, nitrogen, iron, and when the massive ones exhausted their fuel, they expelled those elements in supernovae, seeding the surrounding gas with the ingredients for the next generation of stars, and for the planets that formed around them, and for the chemistry that unfolded on at least one of those planets in conditions that allowed molecules to catalyze their own replication. The chemistry became biology. The biology, across timescales that are long by human standards and brief by stellar ones, became nervous systems, and nervous systems became the capacity to model the world. And the capacity to model the world eventually produced, among other things, a mind lying in a dark room, warm under a blanket, aware of the warmth of its own body, the faint heat radiating from skin into the still air, the quiet exchange of thermal energy between a living system and its environment, which is itself the conservation law operating at the scale of a human being breathing slowly in the dark. That warmth is the same energy, not descended from the Big Bang in some metaphorical sense. The same quantity, rearranged through the chain of transformations that connects the first 3 minutes to this moment, wearing the specific form of a body at rest, radiating gently into a room that will be very slightly warmer in the morning for having had someone sleeping in it. None of it was created along the way. The hydrogen that became the sun was not a new hydrogen. The carbon in the body was forged in a star that no longer exists, distributed through space in a supernova, incorporated into a planet, cycled through the biosphere, and eventually assembled into this particular configuration by processes that had no intention and followed no plan except the blind preference of energy for lower states and the occasional intervention of chemistry that had learned to replicate itself. The quantity is fixed, the rearranging is everything. The last stars will burn out, the last black holes will evaporate slowly over timescales that notation struggles to express, emitting Hawking radiation into a universe that has grown so large and so cold that the radiation itself is the warmest thing in it. And at that final, unimaginably distant moment, the energy will still be there, spread thin beyond any possibility of use, in the maximum entropy state that Clausius pointed toward in 1865, conserved in full, capable of nothing, present everywhere. Everything that has ever happened was one quantity, finding new ways to arrange itself. It is still doing that now, while you are reading this, while you are breathing, while the warmth leaves your skin and enters the air and becomes the temperature of the room, and the room becomes very slightly the temperature of the night. Let it. That is the whole of it, more or less. 27 chapters from a cannon in a Munich arsenal to the last warmth leaving the last black hole, and the thread running through all of it was one thing, one conserved, indestructible, endlessly rearranging quantity that the universe has been working with since before the first atoms formed. It does not need a conclusion. It is not the kind of idea that requires one. It just settles, quietly, the way the chapters have been settling. This channel exists because of people who decided it was worth keeping. Alison has been here the longest, from early enough that the channel was still finding what it wanted to be. And that kind of continuity means something that is difficult to put into a sentence without it sounding smaller than it is. Matthew M. and Brian Winter have been steady in a way that makes the work feel less precarious than self-funded work usually does. And the other Patreon members, the ones who showed up and stayed, make the difference between a project that survives and one that doesn't. If you want to be part of that, the link is in the description. There is nothing else required of you tonight. The energy that moved through every fire and every star and every thought that has ever occurred in this universe is still moving, still rearranging, still finding forms it has not worn before. The most small portion of it is, right now, doing whatever it does inside a mind that is growing quieter, a body settling into rest, a room holding its temperature against the night outside. That is enough. That is, in the precise sense the law intends, exactly enough. Sleep well,